Okay, guys, let's keep on going. Any questions that you may have? And I hope that you are reading the reading assignment. Make sure that you are reading the reading assignments. And hopefully you start to work on the homework problem. Don't leave it for the last minute. And make sure you do those homeworks. And that's important for learning. And if you have any questions, come and see me. And so we keep on going. So please make sure you keep up with the course. And I would say that also that it would be nice to cover the problem and say this is a problem that Professor solved. Let me see whether I can do it myself. And so that process you will learn a lot. And that is, believe it or not, I tell you one thing. I went to MIT, and if you look at my transcript, I got all A's and difficult courses. And I don't think that I was very a smart fellow. No, I was average student. But my technique of doing the problems, this was my technique. And honest to God, if I follow this technique, it works very nicely. So I would go home and say, I covered the solution, and I said, this is a problem that Professor solved. Or in the exam, when I was preparing myself for the exam, I said, this is a problem that Professor solved. I covered the solution, and I take the paper and pencil, and I went and tried to do the problem. If I couldn't do it, then I look at the solution. I never did that. And so I never went and read like a history book, okay, and say, all right, it makes sense, bunch of making some noise. Oh, yeah, it makes sense. Okay, next page. All right, now I know what is going on. Okay, no problem. Okay, next problem now, no problem. It seems to be okay. Oh, yeah, he multiplied that. Okay, that's not the way to do it. That is not the way to do it, and it never worked for me. It never, ever worked for me. And I tell you one story. When I was taking the qualifying exam at MIT, and I was in my dorm, and then I said, I do not know concept of impulse and momentum and so forth, which hopefully I will start to talk about that today. And so, and I was in my dorm near the tank hall as a Memorial Drive. I jumped on my bicycle, I went to MIT, and I had a qualifying exam on Monday, and this was Sunday. So I jumped on my bicycle, I went to MIT, and I went to my office, and I had a dynamic book. I knew exactly what pages I have to look at it. But this time, instead of solving the problem, I just read it. I just read it. I said, okay, yeah, concept of the conservation of momentum, conservation of angular momentum. Okay, I know what it was. And then I jumped back, my bicycle went back, so I had fun. So the next day, I went, and guess what? The first question on dynamic problem was that impulse and momentum. And they were asking that, I vividly remember that if something is hanging with a two cable, like this, is hanging with the two ropes, and something shoot at this board, which cable is going to break first? And this is basically, later on we will solve this problem, and you have to find was a tension in each cable based on concept of impulse and momentum. And I wrote those equations, and this time I end up with a 6 equation, but I had 7 unknown. I said, what the hell is going on? And I wish I had a hammer in my head and put on my head and said, why didn't I look at that problem very carefully? And the question that the duration of impact is a delta t. Delta t should be given to you. I mean, a student were taking our qualifying exam here, and I told them, and they had the same problem. They came to my office and said, Professor, I have 6 equations, but 7 unknown. I said, well, the duration of impact, delta t should be given to you. It's not unknown. It should be given to you, and that's the reason you have 6 equations, but 7 unknown. And then, because that duration of impact is something that you have to know what has happened. So, but at that time, I didn't know. I thought that duration of impact can be also obtained. And that's the reason I ended. They still gave me 8 out of 10, but I wrote that having this equation, you can go ahead and solve for tension and finding which tension. So I'm telling you exactly that if I had done the problem I had written by pencil and pen, then I would have realized, then I would look at the solution and I say, oh wow, delta t should be given. Then I wouldn't have panic in the exam. So I'm just telling you that if you are trying to prepare yourself for the exam, or preparing yourself for the qualifying exam, or preparing for the exam for this class, the way to do it, cover the solution and do the way. This method worked for me, and I got all A's. And I would be happy to show you my transcript. But do whatever you want. That was a technique. It works for me, and I don't think I was very smart fellow. And believe it or not, material that sometimes is covered over there is much more than what I'm covering here. So I want you to make sure that you do your reading assignment and go over the problem, and hopefully you will be having fun. Otherwise, pretty soon you will panic a little bit. Any questions? All right. So let's go over the problem that we started last time and do a couple of more problems. And then we finish the kinematics of the particle. And then we go to the kinetics of particle, and we keep on going. All right. So last time we said that some problems is very complex, and you need auxiliary coordinate system, and you may need 2 or 3 auxiliary coordinate system depending how the system is moving. And so you would have to have those auxiliary. So, and we said that you have a main reference frame, capital XYZ, and then you may attach some auxiliary reference frame, a small XYZ, and your object is moving relative to this, but this one is moving relative to this. So you could have an object, and something is moving in this object, but the whole object is moving with respect to this. And this is a reference R, O, this is rho, and this is R of the particle. And we said that position is defined with respect to main reference frame as RO plus rho respect to a small xyz. Now, if you would like to have velocity, you have to make a derivative of this expression with understanding what is happening to the vector. Is that vector is being twisted, or vector is not twisted, or the length of the vector is changing, and so forth. And we said that velocity with respect to capital XYZ is equal R dot O plus this vector is moving inside, that it has a velocity. So that's velocity with respect to XYZ. But because your auxiliary reference, if it is twisted, then that rho that is inside of that one is also being twisted. So then you do have additional component, which is omega times rho XYZ. Provided that auxiliary reference frame is being twisted. If auxiliary reference frame is not being twisted, then you do not have that term. And if you want acceleration with respect to capital XYZ, again, you make a derivative. That would be R double dot O plus velocity of this one, AXYZ. But because this velocity with respect to XYZ, it could be rotated, because my main reference frame is being twisted, then you do have omega times VXYZ. Then you do have omega dot times rho XYZ. Then you do have omega times velocity of this one would be rho dot, which is velocity XYZ, plus omega times rho XYZ. And if you put them together, acceleration with respect to main reference frame becomes R double dot O plus AXYZ plus 2 omega times VXYZ, which we said this is a corollary acceleration, plus omega dot times rho xyz plus omega times omega times rho xyz. So these are the second equation which we discussed last time, and this is the first equation for velocity, and you use these two equations to obtain your information. So with these two equations, we start to solve one problem, which we did half of it, but we do it again for it wouldn't hurt. So we said that you do have an astronaut, the head of the astronaut sitting on the chair, on this chair, and somehow the chair is going around this axis, is being rotated, and this is the head of the astronaut, which is 3 feet from here, and this head of the astronaut is rotating with an angular velocity of 7 radians per second around a small xyz here. You can say around this axis, or you can say forget about this one, is attached around this axis being twisted. So that's basically inside of this cabin, and this head of the astronaut going like this. That's rotating like that. So it's going like that with 7 radians per second. This cabin itself, which is at the distance of, we said, is equal to 10 feet from here, is also being twisted like that. So now just forget about astronaut. Just think about that cabin itself. It's doing like this, and that angular velocity, we said, is equal to 20 radians per second. And then the whole thing is being twisted again. And you can think about that. You have a motor here, and motor has a shaft here that comes here, and the motor is twisting. And there is another motor here that is twisting. So you can think about that design. So, and then you do have another distance, which is, I think we said that is 30 feet. And this whole object, and you do have main reference frame, capital XYZ. And this one is rotating around this axis with angular velocity of 10 radians per second and 5 radians per second squared. 10 radians per second and 5 radians per second squared. So in order to find out what is exactly happening to the neck of astronaut, you have to know the acceleration of the head of the astronaut. And that acceleration, it produces a lot of forces to the neck of the astronaut. And that is very important to understand whether his bone is going crushed or bone is not going to crush and so forth. Or anything else you would like to know, the forces that's holding this astronaut, what force is happening, and then whether the material can tolerate that. So the first thing that we were interested, what is the velocity of the head of the astronaut respect to main reference frame. So, and we said for this purpose, you put two coordinate system. One is right attached here to this cabin, a small xyz. You can call it x1, y1, z1. And this x1, y1, z1 is being twisted by this 20 radians per second. And of course, it's being also twisted by the big one, but right now we are not worried about that. Then you attach another one right here, and we can call it x2, y2, z2. And this is basically being twisted by this, and then you do have the main reference frame XYZ. So you write your equation, and you go from one reference system to the two, and then you go to the main. 1, 2, 3. And your master equation that you have to implement, that when you go from one reference to another reference, is this one. Velocity respect to the XYZ is equal to R dot O plus VXYZ plus omega times rho XYZ. That's your master equation. So you implement this equation from one coordinate to another coordinate. So you just say, forget about this main reference frame. This is my coordinate system. This is my coordinate system. So now you can say, okay, velocity at this point. Forget about astronaut. Forget about astronaut. This is your reference frame as if is your main reference frame. And this is O that is attached here, which is second auxiliary reference frame is attached. And this one is simply being twisted here. And this point, it has no velocity with respect to this point. It has no velocity. It just goes around that shaft, and it never changes position. So therefore, R dot O respect to this is, we are implementing respect x1, y1, z1. This is R dot O of that point, and this is Vx2, and this is x1, y1, z1. This is x1, y1, z1. So we implement this equation. So from x1, y1, z1 to x2, y2, z2. That's basically what you do. And he said for this operation, R dot O is equal to 0. And Vx1, y1, z1, forget about all of this rotation, and this is, you are just looking at the cabin. And this guy at this instance, of course you can solve it at every instance. We have to define the Euler angle to find the position, but you can define 3 different positions at any instance you can define it. And this object is simply rotating around this coordinate. And at this instance, which is at the 3 feet, is R omega, and the velocity going in this direction at this instance. And R theta dot, and R is 3, theta dot is 3, and that's at this instance is in the capital J. So you can say R omega, and that is equal to 3 feet. Omega is 7, and the direction of that one is J, negative. So that is minus 21J. And now you said this auxiliary is being twisted respect to here, because this is attached to here. As if this one rotates, my auxiliary which is attached to that box is being twisted. And as a result, I do have omega times rho x1, y1, z1. I have omega times rho x1, y1, z1. And that becomes equal to 20J times rho x1, y1, z1 is a 3K at this instance. And that becomes J times K becomes I, and that becomes equal to 60I. And of course, this I and this I and this I, they are all in the same direction. But theoretically, you are talking about this I2, basically, or I1. So theoretically, you are talking about this omega times rho x1, y1, z1 is in the direction of this I, not this I. But at this instance, all of the I is in the same direction. So now you do have this, and you put them together, and that would be velocity with respect to x2, y2, z2, and velocity with respect to x2, y2, z2 becomes 0 plus minus 21j, and plus 60i. And what is this j? Although at this instance is the same direction, all of the j is same, but we are talking about this j. That is respect to this coordinate, minus 21j. Respect. But at this instance, all of my j is the same, and all of my I is the same, and all of my k is the same. So we write it like that. But you have to understand what vector we are talking about. So that is this velocity, and so that becomes minus 21j plus. So now you implement from here to the main coordinate system. So now you go from, let me erase this one, and hopefully if I need some information, you have it so I don't have to. Now you go from x2, y2, z2 to capital XYZ. Again, your master equation is that velocity with respect to XYZ is equal to r dot O. Again, this time O is here. This is a new O. This is your new O. R dot O. This is a generic equation. But how do you apply this generic equation is very important. R dot O plus V respect to x2, y2, z2 plus omega that x2, y2, z2 is being twisted times rho respect to x2, y2, z2. That's your generic equation. So now you start to say, what is the velocity of this point? Forget about all of this thing. Forget about this twist. This is this point, and this is going with a velocity of the 10 radian per second. And at this instant, it's going to be r omega, and it's coming out of the page, and that is going to be 30 times 10, 300i. So this one, which is a velocity of this point, is being twisted r theta dot e theta, and e theta is basically is coming out of the page in the direction of I. So this becomes 300i. And this time, your I is a capital I, because you are talking about the polarity of that point with respect to x, y, z. Velocity with respect to x2, y2, z2, we already found it, minus 21j plus 60i. Minus 21j plus 60i. Plus omega, no, this omega that your auxiliary reference frame is being twisted, this is this one, not this one anymore. We don't care about this one. This is this one. And this is being twisted with the 10 radian per second, that's 10k, times position respect to this coordinate system. And the position would be minus 10j plus 3k. So now you put them together, and velocity with respect to capital XYZ is going to be 300i minus 21j plus 60i, and k times j is negative I, that become 100i, and k times k is 0. So if you put them together, velocity with respect to main reference frame becomes equal to 460i minus 21j. And all of this distance is a feet, so you better write here feet per second.
Excuse me?
Yes?
Sorry, why do you take the position relative to the like x1, y1, z1 at the end?
Well, the equation says omega times x2, y2, z2.
Right.
This is rho of the particle respect to this coordinate system. Okay? This is your particle, this is your coordinate. So position of particle respect to this coordinate system. That's your generic equation. So now you will go to the acceleration. And your acceleration, again, I need some of these things, and hopefully I remember that, but I write it in some corner, so I don't want to look at my notes. And the only thing that I need is just this velocity, probably vx1, y1, z1. That's all I need. And v respect to x2, y2, z2. That's all I need, these two information. So, but hopefully I remember that. All right? So remember those things. And so now you will talk about acceleration. Now you are talking about acceleration. So again, your generic equation from one reference system to another reference system. You go one at a time. So you go from this coordinate as if this is your main reference frame. So you can say acceleration of the particle respect to x2, y2, z2 is equal to r double dot o. This one is acceleration of this position. R double dot o is here. My o is here. I go from x1, y1, z1 to x2, y2, z2. I don't care about this one. As if it doesn't exist. Is this bother you? Any of you bothers this one? If it's so I put it down a little bit so you can see it. Plus acceleration of the object respect to x1, y1, z1 plus 2 omega, that auxiliary reference frame, which is this one, is being twisted respect to here, 2 omega times v1, x1, vx1, y1, z1 plus omega dot times rho x1, y1, z1 plus omega times omega times rho x1, y1, z1. That's your generic equation. And you go from x1, y1, z2 to x2, y2, z2, and forget about capital X, Y, Z. So again, this position, this is simply being twisted like this, and it doesn't go anywhere. Forget about the astronaut, forget about everything. And this position, you have a shaft, and that shaft is being twisted like this. It doesn't go anywhere. It doesn't go anywhere. Respect to x2, y2, z2 doesn't go anywhere. So this doesn't have any acceleration. This is 0. Now you just forget about everything here. You do have the guy that is sitting here at 3 feet at this instance, and it's going around the circle, and we know that we have a normal acceleration, r theta dot square. If you use polar coordinate system, that says r double dot minus r theta dot square er plus 2r dot theta dot plus r theta double dot e theta. So that is basically you have acceleration in this direction, which is r omega square or r theta dot square, and that's acceleration in this direction, and that would be in the direction of negative k, and that acceleration is r is 3 feet, omega is 7 square, and the direction of that one is a k, and that the answer is negative. So you do have negative minus 3 times 7 square k. Then you do have 2 omega, and omega that you are talking about is this 20 radian per second, 2 times 20j, and the velocity respect to x1, y1, z1, it simply was minus 21j. So if you remember from the previous calculation, velocity with respect to x1, y1, z1 was r theta dot, and the direction was minus 21j. And of course, this is not accelerating, therefore we do not have this term. So this term would be 0, and this term would be 20j times 20j times 3k. So you put them together, that becomes acceleration of particle respect to x2, y2, z2. And that becomes 49 times 3, that becomes minus 147. K. And j times j is 0, and that doesn't produce any contribution. And this one becomes 400 times 3, 1200. Now I have to decide what is that 1200 here is. J times k is equal to I, and j times I is negative k. So that's minus 1200 k. So j times k is equal to I, and j times I is negative k. So that is minus 1200 k. So altogether, it becomes minus 1347 k. Now you try to implement from x2, y2, z2 to capital XYZ. Again, your generic equation is here. Let me erase this one. And unfortunately, we are limited to the blackboard because of online student. And so I apologize for erasing some of the information. So let me erase this one. Now you go from x2, y2, z2 to the capital XYZ. And again, you're always here this time. So now you can say acceleration of p respect to main reference frame is equal r double dot o. Remember these things. R double dot o plus acceleration of p respect to x2, y2, z2 plus 2 omega time v x2, y2, z2 plus omega dot time rho x2, y2, z2 plus omega times omega time rho x2, y2, z2. So this time, this is your auxiliary, this is your main, and that's the generic equation. Of course, we derived this equation for you. We just didn't pop it like that. We derived this one, this equation, but you know you implement it. So now you go ahead. Now you go ahead and try to get all of this information. So now you look at this point, O, and forget about the rest. This is rotating with angular velocity omega and angular acceleration of 5 radian per second squared. So this looks like a polar coordinate system. You do have two acceleration. One is a tangential acceleration, one is a normal acceleration. So if something is going around the circle, and you have tangential acceleration, and you do have normal acceleration. According to that, r double dot minus r theta dot square, er, plus 2r dot theta dot, r theta double dot e theta. This is 0, this is 0. You have two acceleration. You should know that. And one is in the direction of capital J, the other one is in the direction of the I. So r double dot O at this time is equal to minus r 30 feet theta dot square, that's 10 square. And that would be in the direction of the, that's r theta dot square. That would be in this direction. So that would be j. You have acceleration, normal acceleration, and you have tangential acceleration. And you have r theta double dot, and r is 30. Theta double dot is equal to 5, and that direction is I. So all of this thing is r double dot O. 3 r dot square, r is equal to 30, omega or theta dot is equal to 10 square, and the direction of that one is in this direction. And that is clearly is in this. It's rotating, is like on the page of the floor. And then you do have tangential acceleration, which is r theta double dot, and that's this. Plus, this one we already calculated from previous one, and that was minus 1,347 K. So I already had calculated this one. That was minus 1,347 K. So I already had that one. Plus 2 omega, and now omega, that auxiliary reference frame, which is this one, is being twisted respect to here. That is 2 omega is equal to 10 K time velocity respect to x2, y2, z2, and that velocity was, how much was that velocity? If you tell me, I erase it. Respect to x2, y2, z2, what was that? Minus 21j plus 60i. Is that correct? Minus 21j plus 60i. I think that's what I remember. I could be wrong, but I think with respect to x2, y2, z2, that's what we had. Then you do have omega dot. Now you do have 5k. Omega dot this term, 5k, times rho respect to x2, y2, z2. You go minus 10j plus 3k. Minus 10j plus 3k. That's rho x, y. Then you do have the last term, which is again omega. Omega is equal to 10k times 10k times minus 10j plus 3k. That's it. Now you put them together, you multiply and you simplify these things, and then you do have acceleration. So the acceleration in respect to main reference frame, therefore, acceleration of particle P respect to main reference frame becomes equal to this becomes 300j, 3,000. 100 square, that becomes 3,000. 100 times 3, that becomes 3,000j plus 150i minus 1,347k. And now you can say k times j is equal to negative I, and that becomes equal to 420. K times j is negative I, that becomes plus, and 420 k times j negative I. And then you do have k times I is equal to j, and that becomes 1200 k times I is j. Then you do have this number, k times j is negative I, that becomes 50i. And finally you have this one, that k times j becomes negative I, that becomes 100i. And k times k is 0. And k times I is equal to j. So that becomes 1000 j. So if you put them together, and whatever I you have, whatever j you have, according to my calculation, acceleration becomes equal to acceleration p respect to capital XYZ becomes 620I plus 5200J minus 1347K. So that is your final answer. Now you could have solved this problem. Any question? Any question? All right. You could have solved this problem without auxiliary coordinate system. You really don't need to use auxiliary coordinate system. But it's much easier with auxiliary, and I find that it's much easier to solve it that way. But you can simply write the position of the particle respect to main reference frame and keep on making derivatives. Keep on making derivatives. But you have to make sure those vector, how it is being twisted. And we said that if you do have a vector that is being twisted, you have to say omega times that vector. I found it that I have done both methods in my notes. I have it, so not a big deal. But I find that auxiliary is better for a student. They don't make a mistake and they don't get confused, because the other one you have to make sure that when you go to the acceleration, what is each vector still a standard. So I'm not going to go that method, but theoretically you should be able to write a vector respect to main reference frame and keep on making derivatives, and with understanding how that vector is keep on changing, and then you will be okay. All right, any question on this problem? You will get some problem like this in your exam number 1, that you have to attach auxiliary reference frame or any other method, as long as your answer is correct. So, and then you will see. And if the time permit, I tell you a bunch of problems that they have solved in the previous cases. All right, let's solve a couple of easy problems, and then I solve one more. Because everything comes to the velocity and acceleration. When we go to the analytical dynamic, you have to know the velocity. And if you cannot find the velocity, then you cannot do the analytical dynamic. So it is very important you be able to find the velocity. And if you use the direct method to find equation of motion, then you have to know acceleration. And if you would like to know the forces, you have to know acceleration. So without these two things, then pretty much you cannot do the dynamic problem. You have to know those velocity and acceleration. And that's very important that you would be able to. Let's say that you do have a ring here, a ring, and this ring is being twisted. This ring is being twisted around this axis, and you do have some bearing here, and this ring has a radius r. Radius r. Radius r. And you do have a piece of marble, that is moving inside this ring at any instant has angle theta. At any instance has angle theta. So this is rotating with the angular velocity omega, and this one is going up and down of this ring, and somehow you have been able to monitor the position as a function of time, then you know theta and theta dot and theta double dot. So you have to know by some camera system, then you, like this camera that's here, it monitors my position, and if you know the time, it says what's my XYZ at any time. No problem. So that's the camera that you have. So same thing for this system. This system is rotating like this. You may have designed something here. If something goes wrong, this marble comes omega, you increase the omega and hit something and switch off or something like that. You may be interested. So we are interested to know what is the velocity acceleration of this piece of marble. So you can solve respect to main reference frame, and main reference frame is here, x, y, and z. And suppose we are interested at this instance that marble is in a plane of the y and z at this instance. Of course, you can solve it at any instance. So you have to say what is other instance. You can also assign at any instance, so at other position. But suppose I'm interested at this instance, which is in the plane of the capital YZ, but certainly you don't need to be at, you can solve it at any instance. Where is the plate is moving like this, and so the marble is going up and down. You can basically define a coordinate system that is like a phi, that where is that page of the book, and then you can say where is my marble theta, then you know the position. No problem. So again, this problem is not that complicated. This problem is relatively easy, and later on we will solve this problem by understanding the forces involved in this motion and talk about stability and so forth for this object. So we can say that we can attach an auxiliary reference frame to the ring, and that auxiliary reference frame is being twisted. So it is, you have a ring here, forget about marble, and inside of this one I attach an auxiliary reference frame XYZ, and of course this XYZ, it goes around, it keep on rotating, and if I'm sitting in this XYZ on this plate, I see my marble is going up and down with angle theta. So I'm sitting on that one. I do not see that I'm being twisted. Somebody else from the ground sees that I'm being also twisted. But I'm sitting on this room. I have no idea that the building is going around because I do not notice that. Unless I watch with the tree and the tree is there, then I can say, oh yeah. So then I'm respect to ground. But respect to this room, I don't see I'm being twisted. Everything is fixed. You are fixed, I'm fixed. No position change. But if somebody respects to the ground, they say, no, your position is not fixed. You are being twisted. So we are interested to know what's the velocity of this one respect to x, capital X. So, and we attach one auxiliary reference frame. Again, you can say velocity of particle P is equal r dot O plus Vxyz plus omega times rho xyz. So your auxiliary reference frame is attached to here, and you can say r dot O is equal to 0. It doesn't go anywhere. No matter where the disk is going, this position O doesn't go anywhere. So my r dot O is equal to what? 0. Now you are saying that this object is going around the circle, this P, theta, and what's the velocity of this one? What's the velocity of that? What's that velocity? Vxyz. What's that? I cannot hear you. What's that? Come on, guys. What's that velocity? R theta dot. And the direction is in this direction, E theta. And you can decompose that E theta if you want in the direction of the capital Ij if you want at this instance. But E theta is keep on changing at different time. So at this instance, E theta is in the plane of the y and z, but E theta is in different direction at different time. So you may want to say at any instance E theta, and E theta may not necessarily be in the plane of the capital Y and Z. At this instance, yes, it's in a plane of capital Y and Z. But at any instance, it is just simply tangent to that circle. Where is the circle here? And that's tangent. Where is the circle? That's tangent. Where is the circle? Is tangent. So that's basic tangent. But at this instance, is in the plane of Y and Z. So I write it E theta. E theta. So that's R theta dot E theta. And at this instance, not at any other instance, at this instance is in the plane of Y and Z. If you would like to decompose this E theta in terms of capital J and so forth, be my guest. And the lines are mutually perpendicular. This is perpendicular to this, and this is perpendicular to this. So the lines are mutual, and so this angle is also theta. So you can say at this instant, this becomes cosine theta capital J plus sine theta capital K, if you want. But I will leave it like E theta, that make sure it is in different direction. It's not necessarily in the J and K all the time. It's not. Then you do have 2 omega. Then you have omega. My auxiliary reference frame is being twisted. That is omega K. And rho xyz is this rho. And rho xyz, you can say RER. RER. At any instance. RER. So you see that I have mixed lots of different coordinate systems. RER. If you would like to say at this instance, your rho is equal to R sine theta J, R cosine theta, R minus R cosine theta K. Be my guess. But I like to say when it's some, this is at any instance. This does not mean at this particular time. When we say E theta at any instance, when I say ER at any instance. So it doesn't make any difference. So now this one, K times ER, and what is a K times ER? This is a vector K. This is vector ER. And can you tell me what's a K times ER? What's that? Well, so let's write it that one. So I'm doing at any instance. So that would be omega R omega. And K times ER, you have to multiply by sine in between. And the sine is pi minus theta. And sine pi minus theta is sine theta. So that's sine theta. And the direction of that one is K times ER is in the direction of a small I. A small I is always normal to the page of that disk is a small I. And a small I is always so your velocity, why this acceleration? So your velocity respect to main reference frame is R theta dot E theta minus R omega sine theta small I. Now let's see whether this makes sense. This makes sense. Theoretically, if you are rotating something, you do have some velocity here, which is R theta dot. That you should understand. But when you are rotating this point, it goes around the circle like this. It goes around the circle. It goes around the circle, and the velocity is equal to R omega. Your R is really this distance, which is R sine theta. Omega is this omega, and because it's rotating like this, it's going in the direction of perpendicular to the page. Perpendicular to the page, which is the direction of negative I. So that makes sense. So you do have two velocity. One is going around the circle, which is R theta dot E theta. And then you do have one more velocity, which is going around the circle like this. And at this instance, it's trying to go like this. And that's r omega. But your r is this distance, because it's going around this circle. Around this circle. And at this instance, is perpendicular to the page. And that's in the direction of negative I. So that is the velocity with respect to main reference frame. If you want acceleration, then he said, no problem. My generic equation is, acceleration of point P is equal r double dot O plus AXYZ plus 2 omega times VXYZ plus omega dot times rho XYZ plus omega times omega times rho XYZ. That's your generic equation. Well, again, for this problem, I do not have this. Now you just look at this disk, this particle, forget about rotation of the disk, and this particle is going around the circle. You do have two acceleration, r theta double dot and r theta dot square. So you do have two acceleration. One is r theta double dot, one is r theta dot square. So AXYZ is simply r theta dot E theta minus r theta dot square ER. So that's that acceleration. You do have two acceleration. Then you do have 2 omega, and your auxiliary reference frame is being twisted by big omega. That's a 2 omega k. And VXYZ was r theta dot E theta. So that is take care of this term. I do not have omega dot. My auxiliary reference frame is not being accelerated. And then I have omega times rho XYZ and omega k times omega k times rho ER or RER. Question? The monitor? Monitor does not go down further than this. So unless I break it and no system comes after me. So is that okay right now? It's better? But then this guys may be in trouble. Are you okay? You are okay? So I will try to write it a little bit up this time. So you do have acceleration with respect to a small xyz, r theta double dot and r theta dot square, which is this. Then you have 2 omega vxyz, 2 omega that auxiliary reference being twisted, times r theta dot e theta. And then you have omega k, omega that we don't have that one, omega k times rho. So now you just have to multiply this, and I find it out based on my experience. Some students have difficulties to figure out all of this vector, and it shouldn't be. So, so you shouldn't have any problem to use your right hand and see what is that vector is. Make sure you know that you use your right hand for the cross product. And I also mentioned at the first day of lecture, I mentioned cross product and the dot product. Hopefully you would be okay. But I find that some students, they have a difficulty to use right hand. Maybe they are left-handed, and that's the reason that they cannot use the right hand. So you can say acceleration of P respect to main reference frame is equal to r dot O, r double dot e theta, r theta dot square ER. Then we have 2 omega r theta dot, 2 omega r theta dot. And now you have to say it was a k times e theta. So this is your k. This is your K. Maybe I show you. This is your K. At any instance, this is your K, and that's your E theta. And this angle is how much? Pi over 2 minus theta. So this angle is pi over 2 minus theta. So this angle was a theta before. This angle. So now you tell me what is a K times E theta. K times E theta is equal 1 times 1, sine in between, which become cosine, and the direction of that one is what? The direction of that one is what? What's that? I cannot hear. I'm an old man. If you would like to say something, say loud. What is that? Negative I. K times E theta is negative I. So that would be negative, and you multiply by cosine theta I. So that takes care of this term. Then you do have omega times omega k, R E R. Let's write that one R omega square. R omega square first. Then you have to say K times ER. This time your K is here. Your K is here. Let's erase this one. And ER is here. That's your ER. K times ER. And that becomes what? K times ER. That's ER. K times ER becomes what? K times ER becomes a sine in between. And sine in between is, this is, sine in between. How much is the sine in between? So that's a theta. This pi over two, this pi over 2 minus theta, and this is pi. So that becomes 180 degree minus theta. 180 degree, pi minus theta. So this angle is pi minus theta. The whole angle is pi minus theta. So this angle is the theta, this pi over 2 minus theta, this is 90 degree. So pi over 2, 9, that's correct. Or you can say pi over 2 minus theta plus another pi, so pi minus theta. And so this K times ER becomes sine in between, and it becomes sine theta. Sine theta. And the direction of that one, negative I. Negative I. So this multiplication inside this parenthesis becomes negative I. And K times I becomes K times I becomes J. K times I becomes J. So this becomes sine theta, and the direction of that one, J. So you do have one acceleration, which again it makes sense because that's tangential acceleration, that's normal acceleration, r theta dot square, and r is a sine theta, and the direction of that one is toward the center, which makes sense again. So you can say acceleration of P respect to xyz is equal to r theta double dot E theta, r theta dot square ER minus 2 omega r theta dot cosine theta I minus r omega square sine theta, the direction J. And at this instant, you can go ahead and say what's the ER and what's the E theta, and I'm not going to entertain that. So you should be able to do that. But make sure you know how to do the cross product and use your thumb to see where your thumb is going. Any question on this problem? All right. Let's see how much time we have. Maybe I can do one more problem, because this business of the velocity is important. Now, if you do have a rigid body, this is all particle. This is all particle. If you do have a rigid body, and this rigid body is a rigid body, and this is a point O, rigid body, is a rigid body, and this rigid body is moving in the plane of XYZ or in the space of XYZ, and maybe it's also being twisted, flipping, and its angle respect to a small x, a small yz is changing, so it is basically, it has some omega here as a result, and this is a reference point P. That's a rigid body. Rigid body is the same as particle, except it's a collection of particles. So if I ask you what is the velocity at point P respect to main reference frame, you say no problem. And if I have attached some auxiliary, maybe here, to this one, then I can say no problem. I can say what's the velocity at point P respect to main reference frame. And according to the equation that we have, velocity at point P of that rigid body respect to main reference frame is equal to R dot O plus Vxyz plus omega times rho xyz. So that's the equation for rigid body, or any particle, anything. That rigid body is a collection of particles. And this is point O. So the velocity at point P is equal to R dot O. What is Vxyz? What is Vxyz? What is Vxyz? Huh? Zero. We never change. Never change. Well, you have two avenues. You can say that this is being twisted here, or I can say the particle is being twisted. So you could have a fixed this one and object rotate respect to XYZ. But if you say that basically the point P respect to a small XYZ never moves, never move, and all of the rotation is associated with a small XYZ, so you have two methods of thinking. So you have to say this is zero, and you just have omega times rho xyz. Your term is reduced. You could have thought a little bit differently, and I will mention. This time I have attached XYZ here, and XYZ is being tumbled. XYZ is being tumbled with the rotation. But you could have another way of thinking too, and I will mention that. Dynamic is something that you have to fall in love. And you have to say, what the hell is going on? Yeah, and you have to say 3 times. What the hell is going on? What the hell is going on? What the hell is going on? If you just say 1 time, is not enough. You have to say 3 times. And then you have some understanding, and then you would be able to solve the problem. Of course, our foreign students do not understand what I'm talking about, but that's okay. So, acceleration, your generic equation is R double dot O plus AXYZ plus 2 omega Vxyz plus omega dot times rho xyz plus omega times omega times rho xyz. So that's again your generic equation when you do have auxiliary. Again, this becomes acceleration of point P respect to main reference frame becomes R double dot O. But this point respect to here is fixed, never moves. It's like my eraser. If this point is fixed to the eraser and my coordinate is attached to this eraser, this point respect to this coordinate system that's attached here, it never moves. It never, the whole eraser is moving, but respect to this eraser never moves. So therefore, you can say this is 0. Same thing, this is 0. And the only term that's left here is omega dot times rho xyz plus omega times omega times rho xyz. So that is again, it comes from the particle, except we understand for rigid body, something respect to another coordinate system never moves. Never moves. Therefore, two terms are going to be 0. This term and this term would be 0. This is basically R dot O is called translation. The object is moving like a translation. That's one term. It's moving everywhere is translation plus rotation. So that is object is moving like that. So you do have a translation plus rotation. So velocity is translation, and this is like my eraser. My eraser goes from here to here, here, here. No rotation. You see that it hasn't rotated. Then you have additional rotation. So then you do have translation plus rotation. That's what you have seen in your undergraduate courses. That said rigid body motion has translation and rotation. Here we demonstrate. All right. So I wanted to mention this thing as well. So you will be okay. All right. And we come back to this rigid body when we go to develop kinetics of rigid body. Then we need to know acceleration, and we talk about these terms. So this is not something that I just throw it here. All right. Let's do one more quick problem. I just want to make sure that you are quite comfortable with the rigid body and the auxiliary coordinate system. I don't want to give this problem that I gave last year in the exam. So I do it this one later for you. And please, at any time that you do not understand, raise your voice. I would be happy to answer your question. Okay, let me see. I will solve all of this problem later on for you. All right, let's do this problem. This is a relatively straightforward problem, but I may do another problem for you. I don't know whether I solved this problem for you. And this is what I gave in exam a while ago. So we have a rod here. There's a rod. This rod has a bearing. You have attached some motor here, and it rotates this rod. And the rod is rotated with angular velocity omega dot 1 and angular velocity omega 1. To this rod is attached another rod with the length AB equal to L. Length L is equal to L. Then we have attached, let's call this one A, this length A. And you can put any number you want. And then you have attached another arm to this one, and you have attached a motor here. There's a motor here, motor here, which is, and this motor, it has a rod is coming out of it, and it has something like this, and it has something to grab. So this is grabbing some particle here. And so you do have a motor here, and this one is rotating. And this is rotating with angular velocity omega 2 and omega dot 2. And this length is equal to B, and this length is equal to C. And sometimes we are interested, and that is rotating with omega 2 and omega dot 2. And I have all of the dimension, and suppose you have all of the omega and omega dot 1, omega dot 1, and so forth that you have. And this distance is a C, and this distance from here to here, let's say, is D. So you have all of the dimension, possible dimension, and we can even put some number for you if you want. This is 0.1 meter. 0.1 meter. This is also 0.1 meter. This one from here to here is 0.2 meter. And this one is equal to 0.4 meter. So, and this is basically a simple machine. It's rotating like this, at the same time it's going around. And you can think about it. You can think about it that, can you give me some application of this device? Can you give me some application of this device? That where do you possibly would design such a machinery? Can you give me some example? You are going to be engineer. And where do you think that this kind of machine would be, you would be using that? Huh? Where do you use this kind of machine? So something is rotating like this, at the same time it's going around the circle. Where do you think you can possibly think about some application of this kind of machinery? Huh? Car? That's very true, actually. The tire of the car, it goes in this direction, then you rotate around circle. That's correct. That's correct. Can you give me a little bit simpler than that? So rather than car. I mean, car is good, but can you give me something simpler? So suppose there is a bug here, and I want to kill that bug, and I rotate this bug here, and I spray all across this room. But I want to spray the other side too. So I take my device and I rotate it and I spray like this again. So that's basically that device. You can think about bug spray. So you have something that is spraying bug like this, and it just does this area, but then around this neighborhood. So anything around here, it does rotation like that. And so then I would like to, then I come here and I rotate it the same. Then I go here and I rotate the same, and I rotate here. But it's great, maybe. So we have a lot of arguments more. So maybe you design something. But nevertheless, or you're maybe holding a device for delivery or something like that, and you want to make sure that this object that's here is not moving. So anyway, we are not talking about actual design right now, but you can bring some application. What happens? It fell down. Okay. So we are interested, you tell us what is the velocity and acceleration of this one. You can say at any instance, or at this instance, which is this object, is in the plane of the blackboard. But you can say at any instance. You just have to know at this instance is here on the page of blackboard. Next time is here. When it rotates, this one rotate. So then you do have another thing that rotates. So you have basically 2 degrees of freedom type situation. So you can say where it is at any instance. You can find it. But at this instance, the object is located like this. We are interested what is the velocity of this one. But if you can define any angle and any angle in this way, then you can basically find at any instance, at any time. But at this instance, we are interested respect to the main reference frame, capital XYZ. At this instant, that everything happens to the blackboard. So you can say, no problem. Do I have a problem? No, I don't have a problem. So, and this looks very complicated motion. One motion like this, then the next motion is going like that. This is simpler than the previous problem that I solved for you. But it doesn't mean. So you may want to use auxiliary coordinate system. Auxiliary coordinate system. Where do you attach auxiliary coordinate system? Where do you would like to attach the auxiliary coordinate system? Where do you attach it? Huh? Let's call A, B, C, D, and actually this is a particle P. We call it particle P. Where do you attach auxiliary coordinate system? At point B. You want it to point B? You can attach at point B, or you can attach at, let's attach at point B. Let's say this is a small XYZ. So now you said, okay, no problem. No problem. My generic equation for velocity at point P is equal to R dot O plus Vxyz plus omega times rho xyz. That's my generic equation. And this time I have only one auxiliary. Previous problem that I solved for that astronaut, it was 2 auxiliary. And sometimes you may have 3 auxiliary and keep on going from the last one to the first one. This is only one auxiliary, so therefore this is the equation. And then you say velocity point R dot O, O is here. And this position, forget about the other rotation. As if this point is here, and this is rotating respect to it. You say R omega, and R omega 1, which is 0.4 meter, times omega 1, and the direction of that one is in direction of negative I. So this R dot O is minus 0.4 omega 1, and the direction of that one is in direction of I. Now you said Vxyz. Now just forget about this rotation. This is going like this around the circle. And at this instance, again, velocity is R omega. What is R this time? 0.1. What's the omega at this time? It goes around the circle. It's omega number 2. So then you do have 0.1 omega number 2. And the direction of that one at this instance, again, is negative I. Then you do have omega, which my auxiliary reference frame is being twisted, times rho xyz, and rho is this vector. Rho is this vector. So that is omega 1k times rho xyz, and rho xyz, you go 0.2 here, 0.1 here in the direction of a small j and k. So you go here 0.3 j minus 0.1 k. So the velocity at point P respect to main reference frame at this instance becomes equal minus 0.4 omega 1 I minus 0.1 omega 2 I, and k times j becomes I, that becomes 0.3 omega 1, k times j is negative I, and k times k is 0. So the velocity at this point becomes all of this thing, you add them up, velocity at point P respect to main reference frame is minus 0.4 omega 1, and this one 0.3 omega 1, this becomes minus 0.7 omega 1, minus 0.1 omega 2 I. And if you know omega 1 and omega 2, you can put the number here, then you do have velocity respect to I. And it makes sense again, because this object is going here, everything is perpendicular to the normal to the blackboard, and that makes sense. That velocity is only in the I direction. Now if you want acceleration of point P respect to main reference frame, let me erase this one. Acceleration, your generic equation here, your generic equation acceleration of P respect to main reference frame is equal to R double dot O plus AXYZ plus 2 omega VXYZ plus omega dot times rho XYZ plus omega times omega times rho xyz. So again, forget about all of this thing. Object is going with omega 1 and omega dot 1, and this position has two acceleration. One is a tangential acceleration, one is normal acceleration. So your tangential acceleration is r theta double dot, which is 0.4 omega dot 1 and the direction of negative I. So this one is minus 0.4 omega dot 1, the direction of that one I. Then you do have r 0.4 omega 1 square, the direction of negative j. That is R double dot O. Then you do have AXYZ. Now this is rotating here again around the circle. It's going around the circle. And again you do have two acceleration. One is R theta dot square. One is R theta double dot. Two acceleration. It's going around the circle, obviously. And the radius of the circle is 0.1 meter, obviously. Forget about the rest of the thing. It is going around the circle. And that is basically what you are doing. And so it's going around the circle, and you do have two acceleration. One is in this direction, one is tangent. And at this instant, the tangent in the direction of negative I, and radial is in the direction of capital K. So you do have two acceleration, and that is equal to 0.1 omega dot 2, the direction of that one I, r theta double dot, and you have r omega square in the direction of Q. And you have 0.1 omega number 2 square, the direction of that one K. That is AXYZ term. Then you do have 2 omega. Now my auxiliary reference is being twisted. My auxiliary reference frame being twisted by this omega. So that's a 2 omega number 1K. And Vxyz, we had that one. Vxyz respect to that one is simply r theta dot. It's going around the circle, and minus r theta dot minus 0.1 omega 1 I at this instance. We did have that one. Omega number 2. Which is this one. Which is this term that we had before. Then we have omega dot 1 K time rho x. Rho is 0.3 J minus 0.1 K. So that's 0.3 J minus 0.1 K. So that's omega dot 1 times rho xyz, 0.3 J minus 0.1 K. Finally, we have omega 1 K omega 1K times omega 1K times 0.3J minus 0.1K. I leave the rest to you. You do the multiplication, summarize it, and see what's the acceleration. So we are pretty much done with the particle, and of course, and rigid body. And rigid body is nothing than collection of particles. And so we are pretty much done with that. So now we go ahead with the kinetics of the particle, and then we go to the kinetic of rigid body, and derive the equation of motion and so forth for arbitrary angle, any rotation, any position, not any instance. So like what we have been doing. So no, any questions? So you can multiply this thing yourself and find the simplification, and we shouldn't do the graduate course, those multiplication. I did already several problems, so all right. So now according to the, so now we go to the kinetics of particle. So what we have for this system, for a particle which doesn't have any dimension here, and the forces applied to this one, F1, F2, F3, and F4, according to the Newton's law, is summation of forces is equal mass times acceleration. And you can apply this equation in the cylindrical coordinate system. You can apply this one in the Cartesian coordinate system. You can apply in the polar coordinate system, and or Cartesian coordinate system. You can apply this equation to any. So the best thing to do that, you identify all of the forces to the particle. You make a picture. You make a picture, and you say this picture is equal to mass times acceleration. You identify inertia. And whatever you do to this picture, you do to this picture. That's the best way to develop the equation of motion. All right? So let's do one problem, then you will understand what I'm talking about. And so to develop the equation of motion, as a result of external forces, what happens to my system? So you identify all of your forces, and you put in one picture. This is indeed like this. F is equal ma. But the way that we do it, that is this is called equivalent system. F, ma. All of the inertia in this term all of the force, and then whatever you do to this picture, you do to this picture. Let's do one problem, then you will understand. And we have about 5 minutes, maybe we're doing one quick problem. Let's say that very simple problem. Let's say that you do have a pendulum with a mass m, gravity is acting, and you disturb this pendulum, or you are applying some forces to this pendulum, f of as a function of t. And this pendulum will start to move. And we are interested to find equation motion at how is the theta is evolving as a function of time. So if you know the force as a function of time, this pendulum is going to displace, and you do have some angle theta, and this theta is changing. And you would like to know how is the theta as a function of time. You know force as a function of time. You do have some equation for the force as a function. You want to know how is your theta is as a function of time. You said no problem. So the first thing that you have to say, if this is a theta, what is the acceleration of this particle? And acceleration of this particle, if the length of this is L, then you can say I have two acceleration. One is a tangential acceleration, one is normal acceleration. So my acceleration is L theta double dot and L theta dot square. That's my acceleration. So now you come and make a picture. You make a picture and you can say, okay, my free body diagram at any instance, I have a pendulum with mg. Gravity is acting. I have a tension T, which is internal force. That's not external force. That's internal to the system. So you are mostly interested in that. And I have a force F of T applied here, which is all the time normal to this F of T that's here. So that's your mg, that's your F of T, and that's a point that goes here. And when we want to develop the equation of motion, we would like to say find a relationship between our freedom, which is theta, and force F. We don't want to bring internal forces to the picture. Internal forces, you may be interested, but not for the equation of motion. For equation of motion, you would like to say the relation between external forces and displacement. If I have this chair and I push it, you are interested in the relation between force I apply and displacement. You are not interested in any other thing. Or there is a pin here, is putting friction here. I'm not interested in that. Those are internal forces. Later on, I may be interested, but not for the equation of motion. So you make a free body diagram. You say, this is my F. Now you make another picture, and you produce your inertia. And your inertia is mass times acceleration, and mass times acceleration. That's all. So whatever you do to this picture, you do to this picture. And I'm interested to find equation of motion. And this angle is a theta. And later on, I developed this one for the rigid body. Much more complex. Much more complex. To develop equation of motion. Again, you are interested in the relationship between forces and displacement and rotation. So what is the best way to develop the equation of motion? The relationship between external forces and theta. What's the best way? I'm not interested to find the T. So you can simply write summation forces in x direction for this picture must be equal to summation forces in the x direction for this picture. Summation forces in the y direction for this picture must be equal to summation. Summation moment for this picture must be equal to summation. The best thing to develop the equation of motion, take the moment of all of these forces with respect to this point. If you take the moment with respect to this point for this picture, the T goes through the point. It doesn't produce any moment. So that becomes Ft times L clockwise, counterclockwise, minus mg times L sine theta. Let me write it down in top. Ft times L minus mg times this distance, L sine theta, So you took the moment of all of this thing respect to point A. You do the same thing for here. You take the moment of all of this thing respect to point A. Again, this goes through the point A. The only thing that has here is ml theta double dot times another L. So now you see that you develop the equation motion. You end up with the differential equation, which is ml squared theta double dot plus mgl sine theta is equal f of t times L. That is your equation motion. And solution to this differential equation will tell you how the theta is evolving as a function of time, subject to some initial condition at the time equals 0. At the time equals 0, what was theta at the time equals 0? What was the velocity? Theta dot. All right, why don't we stop here? And on Friday, we continue on this one. We develop the equation motion for many different systems. Then we talk about stability and so forth. We go from that.